Hey everyone, welcome back to Linear Algebra. This will be part B of lecture 15. And so what we just got done discussing was the way, we had this statement that we just finished proving. We said that the span of S is the smallest subspace of a vector space V containing S. Okay, so the span of S obviously contains S, and it's going to be the smallest subspace of the vector space V that does contain S. All right, so we just got done showing this, or working through this proof. Let's do an example to kind of make this a little more concrete. All right, because I think sometimes when you get kind of caught up in some of these topics, like you can get a little bit the vagueness can be the enemy here. So let's get concrete for a moment. So let's let v1 and v2 be two vectors in R4. Okay. Then by the previous theorem, the span of these two vectors is going to be the smallest subspace of R4. It's going to be the smallest subspace of R4 that contains these two. Okay. So, for example, if V1 is equal to 1, 3, negative 2, 5, and maybe V2 is equal to 0, negative 4, 3, negative 1, right? Then the span of V, or sorry, the span of V1, V2, it's going to be the set, what? A times 1, 3, negative 2, 5, plus B times 0, negative 4, 3, negative 1, such that A, B are real numbers. Right, so it's going to be this set. And this set is going to be the smallest subspace of R4 that contains these two vectors. Right, and this is the smallest subspace of R4 that contains these two vectors. Okay, there's not going to be a smaller subspace than this that contains these two vectors. Okay. All right. Very good. Very good. Okay. Okay. And I'm going to throw out one more theorem, and I'm just going to leave this one to you guys to prove, but this is an interesting consequence of the last theorem that we discussed. And this one says, let's let V be a vector space and S1 and S2 subsets of V. Right, and so the combination here, or the order, so V is a vector space, S1 and S2 are both subsets of V, and we're going to say S1 is a subset of S2, which is a subset of V. Okay. Well, if this is the case, then the span of S1 is a subset of the span of S2. Okay, now how can you prove this? Well, if you think about it, all you need to recognize here is that the span of a subset is itself a subspace, right? So S2 is a subset of a vector space, then the span of S2 is a subspace of V, right? Now, if S1 is a subset of S2, which is itself a subspace now, well, so sorry. S1 is a subset of S2, right? So S1 would have to be a subset of the span of S2, which is a vector space, right? And so the same logic that makes this guy a subset of V is going to be applied to this guy as a subset of the span of S2, right? So basically you can apply the previous theorem and just iterate down to S1. Okay, but I'll leave the proof up to you. Okay, because I want to focus on the next topic related to span. Okay. And so what are we going to do next? Well, what we're going to do next is we're going to introduce a method for simplifying the vectors in the span of a given set. Okay, so our next goal will be to find a simplified form for the vectors in the span of a given set S. Right? So if you think about it, if I'm given a set S that I arbitrarily choose, or maybe I have some reason to choose, I have some subset S of a vector space V. So given S, a subset of V, a vector space. It may be the case that the vectors in S that there may be some redundancy in the vectors in S, for example. Or it may be the case that some of the vectors in S are not necessary to express the full span of S, right? Is there a way to reduce the set of vectors needed to express the span of S? That's the question, right? So can I simplify / reduce the set of vectors that are used to express the span? That's the question. Okay, and the answer is yes, there is definitely a way to do that. And here's how it goes. Okay, so here's how it goes. So suppose S is a finite subset of Rn. There's a little line there. Suppose S is a finite subset of Rn containing k vectors, and we'll say k is greater than or equal to 2. It's pretty simple already if you've only got a single vector. Okay. In the case of a single vector, you could obviously just use a scalar to simplify the vector to the whatever form you like, a non-zero scalar, right? So, okay. So given S a finite subset of Rn containing k vectors with at least 2 vectors, the first thing we're going to do is we're going to form a k by n matrix. Form a k by n matrix A by using the vectors of S as the rows of A. Okay, and so what does that mean? Well, it just means that the span of S is the row space of A. Right, and we talked about row space earlier, and it turns out that if you take the vectors of S and you toss them into a matrix like this, where each of the rows is a vector from S, then you've converted the span concept into the row space concept, like in one fell swoop, just that simply. Okay, and then so that's step one. Basically, take all the vectors in S, toss them into the rows of a matrix A. Okay, so step two then is we're going to row reduce A, right? So we're going to let C equal the reduced row echelon form of A. Okay, and then finally, then a simplified form of the span of S is given by, sorry, on the page here, then a simplified form of the span of S is given by the set of all linear combinations of the non-zero rows of C. Okay. And so basically row reduction has this nice property of filtering out the unimportant vectors of S. Right? So some of the vectors in S, as I said, they may be redundant or they may be unnecessary for other reasons for expressing the span of S. And so this row reduction, right, row reducing the row A, where A is comprised of rows based on S, this row reduction technique tends to filter out the vectors that don't matter. Right? And it'll leave you with a new set of vectors that just like before, can fully express the same span as the original vectors. Okay, so let's do an example. Let's walk through an example here. So let's let, okay, so I'm going to come up with 4 vectors in R4. So 1, 4, -1, -5, 2, 8, 5, 4. -1, -4, 2, and 7, and 6, 24, -1, and -20. Right, and so this is my subset of R4. Right, and so maybe I want to simplify the vectors used to express the span of these 4 vectors. Okay. So what does it mean, right? So if this is my subset of R4, then by definition, right, the span of S is equal to A times the first vector 1, 4, -1, -5 plus B times second vector 2, 8, 5, 4 plus C times the third vector, -1, -4, 2, 7, plus D times the fourth vector, 6, 24, -1, -20, such that A, B, C, D are real numbers. Okay, so that's what the span means, right? So I've got, any linear combination of those 4 vectors is a vector inside the span. Right, but is there a simpler way to express the span than this? Like, do I need 4 vectors to express the same set? I don't know. Let's see. Right, that's the question. Right, so I want to use this. I want to apply this method. So first thing I need to do is I need to create A. Right, so A is going to be equal to a K by N matrix, where K is the number of vectors in S, and N is, of course, in this case, the dimension of the vectors, right? And so each of these vectors is going to be plugged into the row of A. So 1, 4, -1, -5, and 2, 8, 5, 4, and -1, -4, 2, 7, and 6, 24, -1, -20. Okay. So these rows, obviously, you saw me do it, they come out of the vectors of S. Now I'm going to row reduce this matrix, and I'm not going to do it, but you could do it, and you'll see that you could reduce this matrix when you put this into RREF. Okay, well, once we put it into RREF, what we get is 1, 4, 0, -3, 0, 0, 1, 2, and then 0, 0, 0, 0, 0, 0, 0, 0. And that's the matrix we called C in our previous rundown of this methodology. Okay, now we had a theorem a while back when we talked about row space. We said that if A is row equivalent to B, then the row space of A is equal to the row space of B. That's what we said back in our theorem. We proved that. It's back in section 2 something. Right, so we're just going to apply that here. Okay, so the row space of A, the row space created by these 4 rows, is equivalent to the row space created by these 4 rows. Right, and we saw in the first section that basically the way we created this row space is by plugging in the vectors that are in S. Right, and so what does this imply? Well, it implies that the span of S can be expressed using just 2 vectors instead of 4. So the span of S is equal to the set A times 1, 4, 0, negative 3 plus B times 0, 0, 1, 2. Okay, and so these two here are the same set, right? But obviously this one is simpler. You've got 2 vectors needed. Here you've got 4, right? You started with a set S that had contained 4 vectors. It turns out some of these are redundant and unnecessary, right? And that's what this process sifts out. Sifts out which of these can be gotten rid of, and it also at the same time makes the vectors into the simplest, like i.e. smallest values as components. Right? So it simplifies it down. Okay. Perfect. Very nice, right? So I can express the same set, right? So this is again the same set. However many vectors are in the span of S up here are in the same is the same as the span of S down here, right? Exact same set. And both of them are, subspaces of the vector space V, and both of them have all the properties of a vector space. They're exactly the same, which is amazing, right? Amazing that you can do this. Relatively simple, right? Just plug it into the row space, row reduce it, and the new non-zero rows are the best they're the best way to express the span. All right. Perfect. Let's do an example of this. Another example. Let's do another example. Something a little more unusual, right? Let's go back and revisit our polynomial examples. So let's let S equal the polynomials 5x cubed plus 2x squared plus 4x minus 3. That's our first polynomial. And then I'm going to write it on a separate line. Negative x squared plus 3x minus 7. And then 2x cubed plus 4x squared minus 8x plus 5. And then x cubed plus 2x plus 5. Okay, so we'll call this our subset S. And this is obviously a subset of a polynomial vector space P3, right? 3 is the highest order term here. So this set S is a subset of the vector space P3. Now let's find a simplified version of S that can still be used to represent the span of S. So let's find a simplified way to express the span of S. Okay, so that's what we're up to here. So first thing we want to do is we want to re-express S as vectors. It's just easier to work with them, and plus we need to plug them into a matrix, don't we? So S is really polynomials, but we can think of the coefficients of the polynomials as representing individual components in a vector. So 5, 2, 4, negative 3, 0, negative 1, 3, negative 7, and 2, 4, negative 8, 5, and 1, 0, 2, 5. Okay, so remember, this is 5x cubed plus 2x squared plus 4x minus 3. This is 0x cubed minus x squared plus 3x minus 7, right, and so on. All right, so it's the same, you have the same information here as you previously had. All right, so we'll plug that into A. So I have 5, 2, 4, negative 3, 0, negative 1, 3, negative 7, 2, 4, negative 8, 5, 1, 0, 2, 5. And I'm going to row reduce. And when I do that, I get 10, 20, 0, 1, negative 3, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, this is reduced row echelon form. We have to go all the way to RREF. Okay. And so the span of S can be written as A times the first row, 10, 20, plus B times the second row, 0, 1, negative 3, 0, plus C times the third row, right? And then D is just all 0, so we don't, it's not important, and we can just leave it off. Okay. And so the span can be written like that. Now, of course, we started with polynomials, so let's convert this back to polynomials. So you could write it as A times, now this is x cubed plus 2x, right? And then x squared minus 3x. And then this is just C times the constant term. Okay, and that is a simplified version of, a simplified expression of the span of S. Right, remember we started with 4 polynomials and we have boiled it all down to basically 1, right? I mean, we've written it as 1, but it really is 3. There's really 3 different ones here. Okay, perfect, perfect. All right, and let's do one last example, I think, and then we'll call it quits on the span. The last example I want to do is I want to start with a matrix A, and we're going to dig out what the eigenspace looks like, and then talk about the eigenspace and span here. So let's let A equal 0, negative 6, 3, 2, negative 13, 6, and 4, negative 24, 11. Okay, and so starting, this is just the matrix A. We, using this matrix, we can calculate the characteristic polynomial, right? So we can derive the characteristic polynomial. Right, it takes some work, right? It involves identifying the determinant of ax minus lambda x, right? And so it takes a little bit of work here, but we can do it. And what we get is PA of x equals x cubed plus 2x squared plus x, and that's going to be factorable down into x times x plus 1 squared, right? And so from this, we can see that there's 2 distinct eigenvalues, and the one we're going to be interested in is lambda equals negative 1 as an eigenvalue. Okay, there's also lambda equals 0, right? And lambda equals negative 1 has multiplicity 2, so we would expect there to be 2 of them there, right? And so what we want to do is we want to find the eigenvectors for this guy. And so let's see. We can solve the homogeneous system, right? And so the way we have to set this up is we'd say it would be negative 1, so it's lambda I minus A, so lambda is negative 1, and then this would be I3 minus A times the vector x equals the 0 vector. That's the homogeneous system we're interested in. And what this will do is it'll spit out the eigenvectors for lambda equals -1. And that's basically going to dictate the eigenspace, right? Okay, so let's do this. Well, let's set it up anyways. Okay, so -1 times I3 minus a. Well, first we got to calculate that. So that's -1, 0, 0, 0, -1, 0, 0, 0, -1, minus the a vector was 0, -6, 3, 2, -13, 6, 4, -24, 11. Okay, and so when we go through this, we'll get what? -1, 6, -3, -2, 11, -6, and then -4, 24, -12. Okay, so we get this guy here, and then we just have to solve -I3 minus a augmented with 0. We got to solve this and basically just row reduce it by row reduction. Okay, and so it'd be -1, 6, -3, -2, 11, -6, -4, 24, -12, and then 0, 0, 0. Homogeneous system, right? Right, and so we can row reduce this using the normal row operations, and we want to put this into RREF. And what do we get? Well, when you go through it, you get 1, -6, 3, and then a bunch of zeros. Okay, in this case, a bunch of zeros. Okay, and so again, I'm kind of jumping over these steps. You can pause the video, confirm that this is indeed what happens. And then what you can see from this is that the eigenspace, E of -1, it's captured all by this top row, isn't it? Right, and you can kind of go through and figure out what this looks like, but essentially the form of the eigenspace is going to be this. It's going to be 6b minus 3c, right? That's the first component. The second component is b, it could be any real number, and the third component is going to be c, right? B and c are independent, right? The first component is the only one that's dependent, right? So whatever you plug in for b and c, it dictates what the first component is. Okay, and so it's interesting because there are other ways to write this, and so let's look at this. I'm going to kind of write this upright instead. I think a lot of the structure of vectors tends to be more readily apparent when you write them like this. I don't know if that's actually true or not. It certainly feels like it to me, right? And now, one of the things you'll notice is that there's a way to re-express this vector so that b is a scalar and c is a scalar. So you'd have to write it as two separate vectors. But it's easy enough to see how to do that, right? I can write this like this. 6b, b, and 0 plus -3c, 0, and c. All right, I can do that. And from that, you can see that I could write b times 6, 1, 0 plus c times -3, 0, 1. Right, like so. Now, kind of following along with what we previously discussed, we can see here that S is just going to be the set 6, 1, 0 and -3, 0, 1. Right? And what are these two vectors? What are these two vectors? These are the eigenvectors of lambda equals -1. For A. Okay? These are the eigenvectors for lambda equals -1 of A. the eigenvalue is -1. These are the eigenvectors. Okay, and so this procedure that we just discussed can also be used to spit out the eigenvectors. Okay, beautiful, right? Very nice. Right, so this is kind of an end-to-end, starting with A, how can we get to the eigenspace? Well, we can use the same ideas that we've been discussing with the span. Okay, now one last bit of bookkeeping to take care of, and that is, so when we described the span, we said that previously we said that S was non-empty, right? The subset of V, the vector space, had to be non-empty, right? But we can actually extend the definition of span to include the span of the empty set, right? And so that's what this last piece is about. So the span of the empty set is equal to the zero vector. Okay, so this is the definition. So it's defined to be this, but this does make a lot of sense, right? This does make a lot of sense because the trivial subspace, i.e. the zero vector, it's going to be definitely the smallest subspace of any vector space V, right? And hence, obviously, it's going to be the smallest one containing the empty set, right? So there's a lot of, there's good reason to define it this way. Okay, so let's write that down. This makes sense because, this is the trivial subspace, right? The trivial subspace is the smallest subspace of V. It's the smallest subspace of the vector space V, and hence it must be the smallest one containing the empty set. Must be the smallest one containing the empty set. Right? There's lots of you can imagine there are lots of subspaces of V that would contain the empty set, but the span of the empty set would be the smallest one containing the empty set. Right? That's by definition. It follows from our previous theorems, and so this makes a lot of sense. This is hopefully intuitive. Yeah. Sometimes when you're dealing with items related to the empty set, things can lack intuition, but I think this one makes a lot of sense. It's almost like the zero vector is sort of inserted into every vector space. It is in every vector space and subspace must contain the zero vector, and so it's natural that the span of the empty set would contain nothing but the zero vector. It's going to have to be the smallest subspace, right, which would naturally be the subspace that contains nothing but the zero vector. Okay. All right, so I think that is where we'll end it. And in our next section, we will begin to talk about linear independence and get into some of the different ideas that kind of things that we've been discussing. We'll continue to elaborate on in the next section, but we'll mostly be focused on the idea of linear independence. Okay, so until then, take care, and we'll see you soon.